Hi everyone, this is Ting Formosa. So our project is Lidar SLAM. In Lidar SLAM, we use the lidar sensor to explore an unknown environment, and we have to estimate the mapping and the robot location at the same time. So our objective has two parts. First of all, the robot should be able to drive over 20 meters and with at least 180 degrees of turning. And secondly, we have to produce a locally consistent map, which means that the closer laser scan should be able to align to each other. So for the pipeline, we have a front end and a back end. In the front end, we associate both successive and non-successive nodes and use a scan match algorithm to get the observation constraint in order to build the post graph. For backend, we use GTSAM to solve this nonlinear optimization problem. And we have both online and offline optimization. In online optimization, the graph is optimized every iteration. For offline optimization, the graph is optimized after the graph is built. As you can see in this figure, CSN can choose the post that best align the previous lidar scan. We do this by first building a lookup table based on the previous lidar scan, and then we enumerate all possible transformation between the two poses, and then we evaluate their observation likelihood from the lookup table, and as well as the motion model. And finally, we can return this estimated distribution of the transformation. Here are some challenges in our project. So first of all, there are so many components, so it's quite hard to debug. We have to separate out the front end and the back end. And because CSN is quite computationally expensive, so we have to implement a multi-level resolution in order to speed up. And also we narrow down the search space nearby the odometry. And finally, there are also some issues within evaluation because there are no one-to-one mapping between the reference and estimated posts, so we have to do some alignment. So for evaluation metric, there are two issues here. So first of all, there's an alignment issue, and also we have a transformation issue. And the solution that we use, first of all, is a dynamic time warping, which solved the first alignment issue. And second solution is that we use this gradient descent to find a optimal transformation between the two poses so that we can compare different methods. And the metric here is the mean square error loss. Okay, so for in our experiments, we have three settings. The first is simulation, and then rollback, and then real car. In the real car setting, because we don't have the ground truth pose, so we can only do qualitative analysis. And for simulation and rollback, because we have access to ground truth, so we can do both. So for quantitative results, as we shown here, in both simulation and rollback, we can perform better than the baseline after optimization, and it's more obvious, more significant in the rollback scenario. Oh, sorry. And for qualitative results, we compare the trajectory of produced by different methods. And as you can see here, the map, it's more visually appealing after optimization. So yeah, we also have this comparison of the trajectory on the right hand side. You can see here the one odometry produces kind of deviates a lot than other. Okay, so we have done some improvements after the project presentation. What we're responsible for this improvement is, first of all, we find some bugs in our evaluation code, and yeah, we are now able to report more normal numbers. And secondly, we run the algorithm with higher resolutions. So although it takes longer time, but we find out it can produce way better results. Okay, thank you.